And now in this lecture we listen to two questions. In the first question we find out the size of angle PQB is equals to x. We have to find out the value of x, the value of angle x. And in the second question we find out the area of this green shape. So we start with the first question. In the drawing we have a quarter circle. A or B is a quarter circle. This is angle APQ, that is a right angle. Angle AOB is also equal to 90 degrees in its size because AOB is a quarter circle. And we also know that AP equals to PQ. And our task is to find out the size of angle PQB that is equal to x. We have to find out the value of x. So first of all, we'll complete the quarter circle to a semicircle. And we define this point as point M. Okay, this is a semicircle, and therefore AM is the diameter of the semicircle. So I have to know AM is the diameter of the semicircle according to our construction. So AM is the diameter, it is absolutely a straight line. So if we focus on the right side of the straight line AM at point O, here the sum of the angles must be equal to 180 degrees, according to the rule that says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have in the right side of the straight line AM at point O? We have this angle that is right angle, plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its side. In the next step, we will extend line segment PQ by straight line until it touches the semicircle. But the question is where the extended line segment PQ will touch the semicircle. So we will assume that the extended line segment PQ will touch the semicircle at this point L. It is given as the question that angle APQ is a right angle. So if line segment APQ, if angle APQ touches the circle at point L, then actually peripheral angle APL subtend on AL. Again, peripheral angle APL subtend on chord AL. So actually, this is peripheral angle APL that subtend on chord AL. But AL is definitely not the diameter of the semicircle. Why? Because AL doesn't pass through point O, that is the center of the semicircle, and we know that only chord that passes through the center of the semicircle could be the diameter of the semicircle. So AL is not the diameter of the semicircle, and peripheral angle APL subtend on a yield that is not the diameter of the semicircle. It is actually a contradiction to Rule 5. Because according to Rule 5, any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the semicircle. But a yield is definitely not the diameter of the semicircle, so it is a contradiction to Rule 5. So, repeat quickly Rule 5. According to Rule 5, any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the circle. In the drawing we have a circle. This is peripheral angle AOB that is equal to 90 degrees in its size. And therefore peripheral angle AOB must subtend on the diameter of this circle. And AB is indeed the diameter of this circle. So any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the circle. But here we have peripheral angle AP L that is equal to 90 degrees in its size according to what is given as the question, and still it doesn't subtend on the diameter of the circle. It subtends on a L that is not the diameter of the semicircle. So it is a contradiction to Rule 5. So it is impossible that the extended 90 PQ will touch the semicircle at this point L. So we'll assume that the extended 97 PQ will touch the semicircle, will touch the circle at this point L, point H. This is point H, and the extended 97 PQ will touch the circle at point H. Therefore, peripheral angle APH subtend on a edge, peripheral angle APH subtend on a edge, on chord AH. But chord AH is definitely not the diameter of this semicircle because of the fact that chord AH doesn't pass through point O, that is the center of the semicircle. So it is a contradiction to Rule 5 because we have peripheral angle APH is equal to 90 degrees in size and still it doesn't subtend on the diameter of the semicircle. It subtends on a edge that is not the diameter of the semicircle. So it is again a contradiction to Rule 5. So due to the contradiction of Rule 5, we have to conclude that the extended 97 PQ will touch the circle at point M and not in any other point. The extended 97 PQ will touch the semicircle at point M and not in any other point. Otherwise, we have a contradiction to Rule 5. So the external 97 PQ will touch the circle at point M. Now we don't have any contradiction to Rule 5. Why? Because we have peripheral angle APM that equals to 90 degrees in its size and it subtends on AM that is the diameter of the semicircle exactly according to Rule 5. AM is the diameter of the semicircle according to our construction. Repeat again. The extended 97 PQ will touch the circle at point M, and we have here peripheral angle APM that is equal to 90 degrees in its side according to what is given as the question, and indeed peripheral angle APM subtends on AM that is the diameter of the semicircle exactly according to Rule 5. Okay, so in the next step we will join points A and Q together by a straight line. By joining points A and Q, we created the right triangle that is also an associated triangle, triangle APQ. Triangle APQ is a right triangle because angle APQ is right angle, and triangle APQ is also an associated triangle because AP equals to PQ. We know that the sum of the angles in any triangle is equal to 180 degrees. It is true in any triangle, and therefore it is true in triangle APQ. So which angles we have in triangle APQ? But before that, we have the rule that in front of equal sides in a triangle there are equal angles. It gives us the question that side AP equals to side PQ in triangle APQ. So in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. Again, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. So which angles we have in the right triangle APQ? We have this angle that is a right angle, alpha plus alpha is 2 alpha. So 90 degrees plus 2 alpha, and total the sum of those three angles must be equal to 180 degrees according to the rule that says that the sum of the angles in an triangle is equal to 180 degrees. So here we subtract 90 degrees from this equation, and we get that 2 alpha equals to 180 degrees minus 90 degrees, it is 90 degrees. So 2 alpha equals to 90 degrees. Here we divide this equation by 2, and we get that alpha equals to 90 degrees over 2 is 45 degrees. So actually this is angle alpha. The size of angle alpha is 45 degrees. And this is also angle alpha, that equals to 45 degrees in size. In the next step, we prove that those two right angles can go into each other according to side rule. Repeat again, we prove that the upper right triangle AEOQ can go into the lower right triangle OQM according to side rule. So write it down. We have to prove that the upper right triangle AEOQ can went to the lower right triangle OQM according to side rule. First of all, AEO equals to OM. They are both the radius of the circle, therefore they are equal to each other. So if we define the radius of this semicircle as R, then AEO equals to R, and OM is also equals to R. So and I know that AEO equals to OM equals to R. They are both the radius of the semicircle, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, therefore they are equal to each other. So this is angle AOQ in the right triangle AOQ. And it is equal to this angle, that's actually angle MOQ in the right triangle QOM. So if it again, if we found out that angle AOQ in the right triangle AOQ equals to angle MOQ in the right triangle OQM. They are both equal to 90 degrees and therefore they are equal to each other. And finally, this is side OQ, that is a common side that belongs to both triangles. So you can write down that OQ equals to itself as a common side that belongs to both triangles. So OQ equals to itself. It's a common side that belongs to both triangles. So if you prove that the right triangle AOQ can go into the right triangle OQM according to side angle side rule. That is to say, if you prove that those two sides and get the angle that is included between those two sides in the right triangle AOQ corresponding equal to those two sides and the angle that is included between those two sides in the right triangle MOQ. And therefore those two right triangles can go into each other according to side angle side rules. So I write it down. If you found out that the right upper triangle AOQ can go in this is the sign congruent to the right lower triangle OQM according to side angle side rule. And for the fact that those two right triangles can go into each other, we derive that AQ equals to QM, that AQ in the right triangle AOQ is equal to QM in the right triangle OQM. So I write it down. We derive that AQ equals to QM. EQ equals to QM. According to the rule that states that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say AQ and QM, must be also equal to each other and their lengths. So if you found out that side AQ equals to side QM. If you focus on the big triangle MQA, in the big triangle MQM, this is an associated triangle called MQ equals to QA. In front of those two equal sides, we have those two angles that must be also equal to each other and their sizes. So if you define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other. In the next step, I will present to you a new rule and we'll implement the new rule in our drawing. The new rule, it is actually Rule 8. According to Rule 8, an exterior angle of a triangle is equal to the sum of the two interior angles that are not adjacent to it. Again, an exterior angle of a triangle is equal to the sum of the two interior angles that are not adjacent to it. So, in the drawing, we have triangle ABC that could be any triangle. Those three angles, alpha, beta, and gamma, they are defined as interior angles because they are located inside triangle ABC. While this is angle E, angle AC, F equals to E, it is defined as an exterior angle because it is located outside triangle ABC. And according to this Rule 8, the size of the exterior angle E is equal to the sum of the two interior angles that are not adjacent to it. Again, the size of the exterior angle E is equal to the sum of the two interior angles that are not adjacent to it. The interior angle gamma is definitely adjacent to angle E. The two other interior angles that are not adjacent to angle E are alpha and beta. The sum of those interior angles is alpha plus beta, and therefore the size of the exterior angle E is equal to the sum of the two interior angles that are not adjacent to it. That is to say alpha plus beta. Or the exterior angle E equals to alpha plus beta. So we can actually implement Rule 8 in our drawing. Why? Because in our drawing, if you focus on the associated triangle, triangle AQM, those three angles are defined as an interior angles of triangle AQM, while This is angle AQP that is defined as an external angle of the associated angle triangle AQM. And according to Rule 8, the size of the external angle AQP is equal to the sum of the two internal angles that are not adjacent to it. This is angle AQM that is definitely adjacent to angle AQP. The two other internal angles that are not adjacent to angle AQP are those two angles, beta and beta. Therefore, if you found out that the size of the external angle AQP of triangle AQM is equal to beta plus beta. Beta plus beta is 2 beta. So if you found out that the size of the external angle AQP is equal to 2 beta, but we already found out that the size of the external angle AQP is equal to 45 degrees. So we can substitute angle AQP by 45 degrees. And we get that 45 degrees equals to 2 beta. Here we divide this equation by 2. And finally we get that the missing angle beta equals to 45 degrees over 2 is 22.5 degrees in its size. So this is the missing angle beta that is equal to 22.5 degrees in its size. This is also angle beta that is equal to 22.5 degrees in its size. In the next step, we'll focus on the right triangle, triangle OQM. In the right triangle OQM, the sum of the angles must be equal to 180 degrees. So which angles we have in the right triangle OQM? We have this angle that is the right angle, that is associated equals to 90 degrees in its size, plus this angle beta that is equals to 22.5 degrees in its size, plus this missing angle that is actually angle OQM. So the sum of those two angles must be equal to 180 degrees according to the rule that says that the sum of the angles in a triangle is equal to 180 degrees. I repeat again, in the right triangle OQM, 90 degrees plus 22.5 degrees plus the missing angle OQM, in total it must be equal to 180 degrees. So here we subtract 90 degrees from this equation and we get the 22.5 degrees plus the missing angle OQM, in total it must be equal to first of all we have to subtract 90 degrees from this equation. So 180 degrees minus 90 degrees, it is 90 degrees. So in total, if you found out the 22.5 degrees plus the size of the missing angle OQM, in total it must be equal to 90 degrees. So here we subtract 22.5 degrees from this equation and we get that the size of the missing angle OQM is equal to 90 degrees minus 22.5. 90 degrees minus 22.5 degrees is equal to 67.5 degrees in its size. So if you found out the missing angle OQM, this is the missing angle OQM that is equal to 67.5 degrees in its size. We have the rule that says that vertex angles are equal to each other. Angles alpha and beta are defined as vertex angles, and vertex angles are equal to each other. That is to say, angle alpha equals to angle beta. Likewise, we define this angle as 1 and this angle is 2. Angles 1 and 2 are also defined as vertex angles and therefore they are equal to each other. That is to say, angle 1 equals to angle 2 in its size. So, those two angles are defined as vertex angles and not the vertex angles are equal to each other. That is to say, this is angle x that is equal to 67.5 degrees in its size. We should know that x equals to 67.5 degrees in its size according to the rule that says that vertex angles are equal to each other. Again, those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. That is to say, angle x equals to 67.5 degrees in its size. So the answer to the question that this is angle PQB is equals to x, and angle x equals to 67.5 degrees in its size. That is the answer to the first question. So in the next step, I present to you the second question, and we'll solve the second question of this lecture. The second question, our task was to find out the area of this green shape. So in the drawing, we have a semicircle. We know that PQ equals to 10 units in its length. PQ is the diameter, that equals to 10, and therefore the radius of this semicircle must be equal to 10 over 2, that is 5. So I write it down, the radius of this semicircle is equal to 5 units in its length. In addition, inside this semicircle, we have two squares. This is the big square ABCD, and this is the small square MEFC. Again, our task is to find out the area of this green shape. So first of all, we define the center of this semicircle. This point is point O. We join points O and A together by a straight line. Point O is the center of the semicircle, point A is the point of the semicircle itself, therefore OA is the radius of this semicircle that equals to 5 units in its length. Likewise, we join points O and E together by a straight line. OE is of course the radius of this semicircle that equals to 5 units in its length. In the next step, we will define one side of the big square ABCD as A. This is to say, one side of this square ABCD is equals to A units in its length according to our definition. We will define the length of this small line segment OC as X. So, what is the length of the missing line segment BO? BO equals to BC minus OC. So write it down. BO equals to BC minus OC. So BO equals to BC. BC is A, according to our definition. It is one side of square ABCD that equals to A units in its length. Minus OC. OC equals to X, according to our definition. So in total, we should find out that BO equals to A minus X units in its length. This is the missing line segment BO. That is equals to A minus X units in its length. We define one side of the small square MEFC as B. So CF equals to B. EF also equals to B. MEFC is a square, and therefore this angle must be equal to 90 degrees in its size because of the fact that all the angles in any square are right angles. Likewise, ABCD is also square, and therefore this angle must be equal to 90 degrees in its size. So in the next step, I'll copy those two right angles in a new page, and we will implement the Pythagoras theorem on those two right angles. According to the Pythagoras theorem, in any right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So this is the right angle ABO, so I copy this right angle ABO in a new page, and we will implement on it the Pythagoras theorem. So here by PT is the version for Pythagoras theorem. In the right angle ABO, side AB equals to A units in its length. It is one side of square ABCD. Side BO equals to A minus X units in its length. And the hypotenuse AO equals to 5 units in its length. It is actually the radius of this semicircle is equals to 5 units in its length. So actually, this is the right angle ABO that according to the original drawing, according to the Pythagoras theorem, in this right angle ABO, AO squared, that is the square of the hypotenuse, equals to AB squared plus BO squared. So I write it down. This will be equation 1. According to equation 1, AO squared, that is the square of the hypotenuse, is equal to AB squared plus BO squared. The hypotenuse AO equals to 5 units in its length, therefore AO squared is 5 squared, that is 25, and it is equal to AB squared. AB is A, therefore AB squared is A squared plus BO squared. BO is A minus X, therefore BO squared is A minus X squared. So according to equation 1, we have found out that 25 equals to A squared plus A minus A squared. Likewise, we copy the right angle OEF in a new page, and we will implement on it the Pythagoras theorem. Here by PT is a version for Pythagoras theorem. The hypotenuse OF and the hypotenuse OE of the right angle OEF is equals to 5 units in its length. It is actually the radius of the semicircle. Side EF equals to V units in its length. And side OF in total equals to X plus B. So actually, this is the right angle OEF that I copied from the original drawing. According to the Pythagoras theorem, in this right angle OEF, OE squared, that is the square of the hypotenuse, equals to EF squared plus FO squared. So I write it down. This will be equation 2. OE squared, that is the square of the hypotenuse, equals to EF squared plus OF squared. OE is 5, therefore OE squared is 5 squared, that is 25. And it is equals to EF squared. EF is B, therefore EF squared is B squared plus OF squared. OF equals to X plus B, therefore OF squared equals to X plus B squared. So in total, according to equation 2, we should find out that 25 equals to B squared plus X plus B squared. This is according to equation 2, and according to equation 1, we have already found out that 25 equals to A squared plus A minus X squared. So in the next step, we get equation 3 that says that 25 according to equation 1 must be equal to 25 according to equation 2. According to equation 3, 25 according to equation 1 must be equal to 25 according to equation 2. Twenty-five according to equation 1 is equal to A squared plus A minus X squared, and it must be equal to 25 according to equation 2. 25 according to equation 2 is equal to B squared plus X plus B squared. So in total, according to equation 3, I should find out that A squared plus A minus X squared equals to B squared plus X plus B squared. Here we'll open the brackets on both sides of this equation, equation 3, we get that according to equation 3, A squared plus A minus X squared. A minus X squared equals to A squared plus X squared minus 2 times A times X. And it is equals to B squared plus X plus B squared. X plus B squared equals to X squared plus B squared plus 2 times X times B. So here we have X squared on both sides of this equation, so X squared will get cancelled. After you cancel X squared, in this side of equation 3, we found out we have A squared plus A squared is 2A squared plus minus 2x, minus 2ax, yeah, minus 2ax. And it is equals to, in this side of the equation we have, equation 3 we have B squared plus B squared, that is 2B squared plus 2xb. So in total, according to equation 3, I should find out that 2a squared minus 2ax equals to 2b squared plus 2xb. Here we relate 2ax to this equation, equation 3, and we get that according to equation 3, 2a squared equals to 2ax plus 2bx plus 2b squared. So here we subtract 2b squared from this equation, equation 3, and we get that according to equation 3, 2a squared plus 2b squared equals to 2ax plus 2bx. So here we divide this equation, equation 3 by 2, and finally get that according to equation 3, 2a squared over 2 is a squared, minus 2b squared over 2 is minus b squared, and it is equals to 2ax over 2 is ax, plus 2bx over 2 is bx. So in total, according to equation 3, we should find out that a squared minus b squared equals to ax plus bx. We have the famous algebraic identity that says that a squared minus b squared is equal to a plus b times a minus b. And it is equal to ax plus bx. Here we take x out of as a common factor from those two expressions, so inside the brackets we left only with a plus b. So in total, if we found out that a plus b times a minus b equals to x times a plus b. We know that a is the length of one side of square ABCD and b is the length of one side of square MEFC. So a and b they are lengths, and therefore there must be positive numbers. And when you add two positive numbers to each other, the result must be also a positive number. So a plus b is positive, it is a positive number, and therefore it is allowable to divide this equation 3 by a plus b. Because a plus b can never be equal to 0. It must be a positive number. So we divide this equation 3 by a plus b. So in this equation 3 you have a plus b times a minus b, so a plus b will get cancelled. So in this side of equation 3 we left only with a minus b. This is equal to, here we divide this equation by a plus b, so after we divided this equation, this side of the equation by a plus b, so a plus b will get cancelled and we left only with x. So in total, according to equation 3, we should find out that a minus b equals to x. So here we add to this equation 3 by b, and we get that a equals to b plus x. So here we subtract x from this equation 3, and get that according to equation 3, actually we subtract x from this equation 3, so I get that a minus x equals to b. A minus x equals to b. Here we square this equation 3. And we get that a minus x squared equals to b squared. And again, according to equation 3, we found out that a minus x squared equals to b squared. So our task is to find out the area of this green shape. So what is the area of the green shape? From the drawing, it is very easy to see that the area of this green shape equals to the area of the big semicircle minus the area of the big square minus the area of the small square. Again, we should find out that the area of this green shape, that is the area that we are looking for in this question, is equal to the area of the semicircle minus the area of the big square ABCD minus the area of the small square. We know that the area of any semicircle equals to the area of the circle over 2. Therefore, the area of this semicircle must be equal to pi r square, that is the area of the circle, over 2. And again, the area of this semicircle must be equal to pi r square over 2. But we have already found out that r, that is the radius of this semicircle, is equal to 5 units in its length. If r is 5, then r square is 5 squared, that is 25. So in total, pi r square over 2 is 25 pi over 2. 25 pi over 2 square units is the size of this big semicircle minus the area of the big square ABCD. One side of square ABCD equals to A, and therefore the area of the big square must be equal to A square. Minus the area of the small square MEFC. One side of this small square MEFC is equal to B units, and therefore the area of this small square must be equal to B square. So in total, we should find out that the area of the green shape equals to the area of the the area of the semicircle, that is 25 pi over 2 square units, minus the area of the big square, that is equals to A square, that is, to say it is minus A square, minus the area of the small square, that is B square, therefore it is minus B square. Okay. Here we take minus 1 as a common factor from those two expressions, and we get that the area of the green shape in total equals to 25 pi over 2. Here we took minus 1 as a common factor from those two expressions, so inside the bracket we left with A square plus B square. And according to equation 1, we have already found out that $25 equals to A square. 25 equals to A square plus A minus X square. Repeat again, according to equation 1, we already found out that 25 equals to A square plus A minus X square. But we already found out that according to equation 3, A minus X square equals to B square. So we substitute A minus X square here by B square, and we get that according to equation 1, 25 equals to A square plus A minus X square, and A minus X square is equal to B square according to equation 3. So in total we found out that A square plus B square equals to 25. Therefore, we substitute A square plus B square here by 25, and we get that the area of the green shape in total equals to 25 pi over 2 minus A square plus B square, and A square plus B square is 25. So we substitute A square plus B square by 25, so it is minus 25. So in total we should find out that the area of this green shape, that is the area that we are looking for this question, is equals to either 25 pi over 2 minus 25 square units in its size. In terms of numbers, it is equals to 14.27 square units in its size. And that is the answer to the second question. And then again, we should find out that the area that we are looking for in this question, that is the area of this green shape, it is equal to either 25 pi over 2 minus 25 square units in its size. So in terms of numbers, the area of this green shape, it is equal to 14.27 square units. So we finish with the second question. In the next step, I'll summarize the lecture. We'll start with the first question, of course. In the first question, Our task was to find out the size of angle p cubed is equals to x. We have to find out the value of x. So in the drawing we have a quarter circle, AOB is a quarter circle, therefore this angle AOB must be equal to 90 degrees in size. In addition, we know that angle APQ is also a right angle, and we also know that AB equals to PQ. Again, our task is to find out the size of angle P cubed is equals to x. We have to find out the value of x. So in the first step, we completed the quarter circle to a semicircle. Again, we completed the quarter circle to a semicircle. So actually, AM is the diameter of the semicircle according to our construction. And here, AM is the diameter, it is absolutely a straight line. So if you focus on the right side of the straight line, AM is point O. Here the sum of the angles must be equal to 180 degrees according to rule 3 that says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of AM at point O? We have this angle that is a right angle, plus this missing angle, the sum of those two angles must be equal to 180 degrees in the sides according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. And in the next step, we extended line 70PQ by straight line until it touches the semicircle. But the question is where the extended line 70PQ will touch the semicircle. So we assume that the extended line 70PQ will touch the semicircle at this point, point L. And therefore, we have here peripheral angle APL. Peripheral angle APL subtend on AL. Again, peripheral angle APL subtend on chord AL. And because of the fact that chord AL is definitely not the diameter of this semicircle, because chord AL doesn't pass from point O, that is the center of the semicircle. And you know that the diameter of any circle must pass through the center of the semicircle. And AL doesn't pass through the center of the semicircle, and therefore AL, chord AL cannot be the diameter of this semicircle. It is a contradiction to rule 5. Why? Because according to rule 5, any peripheral angle that is equal to 90 degrees in size must pass through the must subtend on the diameter of the semicircle. But APL subtend on AL, that is not the diameter of the semicircle. So it is a contradiction to rule 5. Likewise, we assume that the extended line 7PQ will touch the semicircle and will touch the circle at this point H. So we have here peripheral angle APH, peripheral angle APH subtend on AH. Again, peripheral angle APH, this is peripheral angle APH that subtend on AH. But again, we have contradiction to rule 5 because peripheral angle APH subtend on AH, and AH is definitely not the diameter of the semicircle. Why AH is not the diameter of the semicircle? Because it doesn't pass from point O, that is the center of the semicircle. So due to those two contradictions, we have to conclude that the extended line 7PQ will touch the semicircle at point M and not in any other point. Otherwise, we will have contradiction to rule 5. Now, we know that peripheral angle APM, that is equal to 90 degrees in size according to what is given as the question, subtend on AM, that is the diameter of the semicircle, exactly according to rule 5. Okay? So, in the next step, we join points A and Q together by straight line. So here, by joining points A and Q, we created the right and associated triangle, triangle APQ. Triangle APQ is a right angle because angle APQ is a right angle, and it is also an associated triangle because AP equals to PQ. And we have the rule, it is given as the question that AP equals to PQ. We have the rule that says that in front of equal sides in the triangle, there are equal angles. So in front of those two equal sides, we have those two angles that must be also equal to each other and their sizes. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha because they are equal to each other. We also know that the sum of the angles in any triangle is equal to 180 degrees. It is true in any triangle, and therefore it is true also in the right and associated triangle, triangle APQ. So which angles we have in the right and associated triangle, triangle APQ, we have this angle that is a right angle, alpha plus alpha is 2 alpha. So 90 degrees plus 2 alpha, in total they must be equal to 180 degrees. We have subtracted 90 degrees from this equation, so 180 degrees minus 90 degrees is 90 degrees. So in total we should find out that 2 alpha equals to 90 degrees. Here we divide this equation by 2 and finally found out that the missing angle alpha equals to 90 degrees over 2, that is 45 degrees. This is angle alpha that is equals to 45 degrees in its size, and this is also angle alpha that is equals to 45 degrees in its size. So in the next step, we proved that those two right triangles can go into each other according to sine angle sine rule. That is to say, we proved that the upper right triangle AQO can go into the lower right triangle, triangle OQM. So why those two triangles can go into each other? First of all, side AO of the right triangle AOQ equals to side OM of the right triangle OQM. They are both the right area of the circle, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, side OQ is the common side that belongs to both triangles. So we can write out that OQ equals to itself is a common side that belongs to both triangles. So if you prove that those two right triangles can go into each other according to sine angle side rule. What is sine angle side rule? We actually proved that those two sides and the angle that is included between those two sides in the right triangle AQO are corresponding equal to those two sides and the angle that is included between those two sides in triangle QOM. And therefore those two right triangles can go into each other according to sine angle side rule. Repeat again, if you found out that the right triangle OQ can go into the right triangle OQM according to sine angle sine rule. And from the fact that those two right triangles can go into each other, we will derive that AQ equals to QM. Sine AQ of the right triangle AQO is equal to sine OQM, and sine AQ equals to sine QM. Sine AQ of the right triangle AQO is equal to sine QM of the right triangle OQM. And again, sine AQ equals to sine QM. According to the rule that said that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say AQ and QM, must be also equal to each other in their lengths. In the next step, I presented to you a new rule and we implemented the new rule in our drawing. The new rule is actually Rule 8. According to Rule 8, an exterior angle of a triangle is equal to the sum of the two interior angles that are not adjacent to it. Again, an exterior angle of a triangle is equal to the sum of the two interior angles that are not adjacent to it. This is triangle ABC that could be any triangle. Those two angles alpha, beta, and gamma are defined as an interior angles of triangle ABC because of the fact that they are located inside triangle ABC. While this is angle ACF, this is that is defined as angle E. It is defined as an exterior angle because of the fact that angle E is not located inside triangle ABC, but it is located outside triangle ACF. It is located outside triangle ABC, therefore it is defined as an exterior angle. So what is the size of this exterior angle, angle E? The size of the exterior angle E is equal to the sum of the two interior angles that are not adjacent to it. This is the interior angle gamma that is definitely adjacent to angle E. The two other interior angles that are not adjacent to it are those two interior angles, alpha and beta. So in total we found out that the size of the exterior angle E is equal to alpha plus beta, because alpha plus beta are the two interior angles that are not adjacent to it. So E, the size of the exterior E equals to alpha plus beta according to Rule 8. So we can actually implement Rule 8 in our drawing. So in relation to the big associated triangle AQM, this is angle AQP. This is defined as an exterior angle of triangle AQM. Why angle AQP is an exterior angle? Because it is not located inside triangle AQM. So the size of this exterior angle AQP will be equal to the sum of the two interior angles that are not adjacent to it. This is angle AQM that is definitely adjacent to angle AQP. The two other interior angles that are not adjacent to it are those two angles, beta and beta. So according to rule 8, the size of the external angle AQP is equal to beta plus beta. And again, according to 8, in relation to the big associated triangle AQM, the size of the external angle AQP is equal to beta plus beta. The size of the external angle AQP equals to beta plus beta, this is 2 beta. So the size of the external angle AQP is equal to 2 beta. This is the external angle AQP is equal to 2 beta. But again, angle AQP equals to 2 beta. But we already found out the external angle AQP is equal to 45 degrees. We can subdivide angle AQP by 45 degrees. We subdivide angle AQP by 45 degrees, so 45 degrees equals to 2 beta. Here we divided the equation by 2 and finally found out that the size of angle beta is 45 degrees over 2, that is 22.5 degrees. This is angle beta, that equals to 22.5 degrees in size, and this is also angle beta, that equals to 22.5 degrees in size. In the next step, we focus on the right triangle OQM. In the right triangle OQM, the sum of the three angles must be equal to the sum of its three angles must be equal to 180 degrees. So which angles we have in the right triangle OQM? We have this angle, that is the right angle, plus 22.5 degrees, plus the missing angle OQM. In total, they must be equal to 180 degrees, according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. So in the right triangle OQM, 90 degrees plus 22.5 degrees, plus the size of the missing angle OQM, in total, they must be equal to 180 degrees. Here we subtracted 90 degrees from this equation, and found out that 180 degrees minus 90 degrees is 90 degrees. So 90 degrees equals to 22.5 degrees plus the size of the missing angle OQM. Here we subtracted 22.5 degrees from this equation, and finally found out that the size of the missing angle OQM is equal to 90 degrees minus 22.5 degrees, that is 67.5 degrees. So this is the missing angle OQM, that equals to 67.5 degrees in size. We have the rule that says that vertex angles are equal to each other. Angle alpha and beta are defined as vertex angles, and therefore they are equal to each other. Likewise, those two angles 1 and 2 are also defined as vertex angles, and therefore they are equal to each other. That is to say, angle 1 equals to angle 2 in its size. So we can actually implement the rule in our drawing. Those two angles are defined as vertex angles, so in order that vertex angles are equal to each other. That is to say, x equals to 67.5 degrees in size. So the angle that we are looking for in this equation, that is angle x, is equal to 67.5 degrees in size. And that is the answer to the first question. So we finish with the first question. In the next step, I presented to you the second question of this lecture, and we answered on the second question. In the second question, our task is to find out the area of this grand shape. So in the drawing, we have a semicircle. PQ, that is the diameter of this semicircle, is equal to 10 units in itself. Therefore, the radius must be equal to 5. In addition, inside this big semicircle, we have the big square BCD and the small square MECF. Again, our task is to find out the area of this grand shape. So first of all, we defined the center of this semicircle. This point is point O. We join points O and A together by side line. OA is of course the radius of this semicircle, that is equal to 5. We join points O and E together by side line. OE is also the radius of this semicircle, that is equal to 5. That is equal to 5. In the next step, we define one side of this square ABCD as A. So AB equals to BC equals to CD equals to DA equals to A. We define this short line segment OC as X. So what is the length of BO? BO equals to BC minus OC. Again, BO equals to BC minus OC. So BO equals to BC, that is A, minus OC, that is X. So in total, BO equals to A minus X units in its length. We know that ABCD is a square, therefore this segment must be equal to 90 degrees in its sides. Likewise, we define one side of the small square MECF as B. So ME equals to EF equals to FC equals to CM equals to B. So MEFC is a square, and therefore this again must be equal to 90 degrees in its sides. In the next step, I copy the rectangle AOB in an equation we implemented on it the Pythagoras theorem. According to the Pythagoras theorem, in a rectangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is the rectangle AOB that is coming from the original drawing. According to the Pythagoras theorem, in this rectangle AOB, AO squared, that is the square of the hypotenuse, equals to AB squared plus BO squared. Okay. AO is 5, therefore AO squared is 5 squared, that is 25. And it is equal to AB squared. AB is A, therefore AB squared is A squared. Plus OB squared. OB is A minus X, therefore OB squared is A minus X squared. So in total, according to equation 1, we should find out that 25 equals to A squared plus A minus X squared. In the next step, I copied the rectangle EFO in a new edge and implemented the Pythagoras theorem on this rectangle EFO. So actually, this is the rectangle EFO that is coming from the original domain. According to the Pythagoras theorem, in this rectangle EFO, EO squared, that is the square of the hypotenuse, equals to EF squared plus FO squared. Again, EO squared equals to EF squared plus OF squared. EO is 5, therefore EO squared is 5 squared, that is 25, and it equals to EF squared. EF is B, therefore EF squared is B squared plus OF squared. OF is B, X plus B, therefore OF squared is X plus B squared. So in total, according to equation 2, we should find out that 25 equals to B squared plus A, B squared plus X plus B squared. This is according to equation 2. Well, according to equation 1, we have only found out that 25 equals to A squared plus A minus X squared. In the next step, we created equation 3 that says that 25 according to equation 1 must be equal to 25 according to equation 2. And again, we created equation 3 that says that 25 according to equation 1 must be equal to 25 according to equation 2. 25 according to equation 1 equals to A squared plus A minus X squared, and it must be equal to 25 according to equation 2. 25 according to equation 2 equals to B squared plus X plus B squared. So here we open the brackets on both sides of this equation, equation 3, and find out that A squared plus A minus X squared. A minus X squared equals to A squared plus X squared minus 2 times A times X. And it is equals to B squared plus X plus B squared. X plus B squared equals to X squared plus B squared plus 2 times X times B. Here we have X squared on both sides of this equation 3, so X squared we get cancelled. So after we cancelled X squared, in this side of equation 3 we left with A squared plus A squared is 2A squared minus 2AX. While in the other side of this equation 3 we have B squared plus B squared, that is 2B squared plus 2xb. So in total, according to equation 3, we found out that 2a squared minus 2ax equals to 2b squared plus 2xb. Here we added 2ax to this equation, equation 3, and found out that according to equation 3, 2 times a squared equals to 2ax plus 2bx plus 2b squared. Here we subtract 2b squared from this equation, equation 3, and found out that according to equation 3, 2a squared minus 2b squared equals to 2ax plus 2bx. Here we divided this equation, equation 3 by 2, and found out that 2a squared over 2 is a squared, minus 2b squared over 2 is minus b squared, and it equals to 2ax over 2 is ax, plus 2bx over 2 is bx. So in total, according to equation 3, we actually found out that a squared minus b squared equals to ax plus bx. We have the first algebraic identity that says that a squared minus b squared equals to a plus b times a minus b. And here we took x as a common factor from those two expressions, so inside the brackets we left only with a plus b. So in total, according to equation 3, we actually found out that a plus b times a minus b equals to x times a plus b. Because of the fact that a and b are the lengths of the big square and the small square correspondingly. Therefore there must be a positive numbers. And when you add two positive numbers to each other, the result must be a positive number. And therefore a plus b must be a positive number, it can never be equal to 0, and therefore it is allowable to divide this equation 3 by a plus b. So we divided this equation 3 by a plus b. So here a plus b will get cancelled, and we have only a minus b, while on the other side of this equation 3 we have a plus b that also will get cancelled, and we have only with x. So in total, according to equation 3, we should find out that a minus b equals to x. Here we added b to this equation, and we found out that a equals to b plus x. In the next step we subtract x from this equation, and we found out that a minus x equals to b. If a minus x equals to b, if we square this equation 3, we get that a minus x squared equals to b squared. According to, and our task is to find out the area of this green shape. So what is the area of the green shape? From the drawing it is very easy to see that the area of this green shape must be equal to the area of the semicircle minus the area of the big square minus the area of the small square. Repeat again, the area of this green shape must be equal to the area of the semicircle minus the area of the big square ABCD minus the area of the small square. The area of the semicircle equals to the area of the circle over 2. That is to say, it is pi r square over 2. R is 5, therefore r squared is 5 squared, that is 25. So pi r square over 2 is 25 pi over 2. Minus the area of the big square ABCD. One side of square ABCD is a, therefore the area must be equal to the side squared. So it is minus a squared. Likewise, one side of the small square is b, therefore one side is b, therefore the area of the small square must be equal to b squared. So it is minus b squared. So in total we should find out that the area that we are looking for in this question, that is the area of this green shape, equals to the area of the semicircle, that is 25 pi over 2, minus a square minus b square. So here we took minus 1 as a common factor from those two expressions, and finally found out that 25 pi over 2 minus, so we take minus 1 as a common factor, so inside the brackets we left only with a square plus b square. So in total we should find out that the area of the green shape equals to 25 pi over 2 minus a square plus b square. According to equation 1, we actually found out that 25 equals to a square plus a minus x square. So 25 equals to a square plus a minus x square. A minus x square equals to b squared. So we can substitute a minus x squared here by b squared. We did it, and we actually found out that 25 equals to a square plus b squared. So 25 equals to a square plus b square. Now we have found out that the area of the green shape equals to 25 pi over 2 minus a square plus b square. So we can substitute a square plus b square by 25, because a square plus b square equals to 25 according to equation 1. So we did it, and we actually found out that the area of the green shape in total equals to 25 pi over 2 minus a square plus b square, that is 25. So in total, the area of the green shape equals to either 25 pi over 2 minus 25 square units in its size. In terms of numbers, the value of this expression, 25 pi over 2 minus 25, is 14.27 square units in its size. Repeat again, if we found that the area of this green shape, it is equals to either 25 pi over 2 minus 25 square units in its size, or in terms of numbers, the area of this green shape equals to 14.27 square units in its size. Okay, thank you very much.